Right. Hello everyone and welcome back to another IGCSE chemistry video. This is actually part 2 of chemical reactions, and in this video we'll be discussing everything about reversible reactions and equilibrium. So what is a reversible reaction? A reversible reaction is just a reaction where you can change the direction of the reaction by changing certain conditions. So uh, a lot of the reactions that we are used to have a symbol like this, and this is to show that it's a forward reaction. However, reversible reactions are actually denoted with this symbol in red here. It's like two half arrows that are put together. And the reaction from left to right, which is this direction, is called the forward reaction. Whereas the reaction from right to left, which is in this direction, is called the backwards reaction. And over here I have a very common example for a reversible reaction, where if I have hydrated copper sulfate. As I was saying, over here we have hydrated copper sulfate, which upon heating actually breaks down to form copper sulfate, or anhydrous copper sulfate to be exact, and water. Now you can actually use this reaction to test for water, or to test if a liquid is water, because hydrated copper sulfate is blue in color but anhydrous copper sulfate is white. So if upon heating, so if I took anhydrous copper sulfate, which is this one, and I added water to it and it turns blue, which would indicate that it became hydrated as shown here, then that liquid is water. If it remains white, then that liquid isn't water. So this is one of the ways of testing water. Now there's another reversible reaction that involves cobalt chloride that you can also use to test for water, and it's also a reversible reaction. So let me just write that down. Right, so this is the second reversible reaction that can be used to test for water. So over here I have hydrated cobalt chloride, which is pink in color, and upon heating it becomes anhydrous cobalt chloride, which is blue in color, and water. So this tells us that and basically over here you would use a similar method, where if I take anhydrous cobalt chloride, which is blue, and I add water, or if I add a liquid and it turns pink, which would indicate that it became hydrated cobalt chloride, then that liquid indeed is water. If not, and it remains blue, then it isn't water. And so this is another test for water. It's also a reversible reaction, and this is actually something that you're required to know as per the IGCSE scheme. Now, I kind of alluded to this before, but just to clarify, if I have hydrated compounds such as hydrated cobalt chloride, which is this guy, and hydrated copper sulfate, which is this one, then and I heat them up, then I'm basically creating anhydrous compounds, which means that I'm separating the water from the actual, metal compound. And then we already discussed how the addition of water to anhydrous compounds can be used to test for water. And now we should definitely look at some of the conditions that are present, some of the conditions that affect reversible reactions, and also discuss what equilibrium means. Right, so let's look at a reversible reaction under equilibrium, under a closed system where none of the particles can escape, or new particles can't enter. Now over here, let's consider the reaction between nitrogen and hydrogen, which forms ammonia. Remember, it's a reversible reaction, so you use the necessary symbol for that. And ammonia is 2NH3. Now, under a closed system, what happens is that for every 3 molecules of hydrogen, let's just get another color. For every 3 molecules of hydrogen and 1 molecule of nitrogen, you can create 2 molecules of ammonia. And you can see that over here as well. I have 1 molecule of nitrogen and 3 molecules of hydrogen, which together react to form 2 molecules of ammonia. Now, yeah, when this occurs, obviously you need the correct mixture of nitrogen and hydrogen in the closed container. So we have the correct mixture here. Now the question is, will all of the hydrogen and nitrogen react to form ammonia? The answer is no, because it's a reversible reaction. If it wasn't, then yes. Now in reversible reactions in a closed system, in this case what would happen is that once a certain amount of ammonia is formed, the system will reach a state known as dynamic equilibrium. Let's write that down. Dynamic equilibrium, and sometimes people just shorten it to say equilibrium, but dynamic equilibrium is more it's more accurate, let's just say that. So what this means is that okay, let's split the terms, the dynamic and equilibrium. Dynamic means when there's a continual change at the particle level, while equilibrium means there's no overall change. So dynamic equilibrium the term dynamic equilibrium implies that once a certain level of ammonia is reached, while at a particle level, changes are still occurring and more ammonia is still being formed. At the same time, the overall concentration of ammonia doesn't changes. What this means, and to simplify it even further, once let's say X amount of ammonia is formed, every 2 molecules of ammonia now break down to form 3 molecules of hydrogen and 1 molecule of nitrogen. So it's the reverse of what happened before, which means that it's like every time you make one step of progress, you also take another step back that kind of cancels out the progress you made. And that's what dynamic equilibrium is trying to describe. While the overall concentration of ammonia will remain the same, once you reach that level, at a particle level, changes will still occur. And yeah, so again, most people just shorten it to equilibrium, but dynamic equilibrium is preferred. And reversible reactions in a closed system when are at equilibrium when the forward and reverse reactions take place at the same rate. So the rate of reactions for both are the same, and the concentration of reactants and products aren't changing, which is the whole purpose of the closed system. It's so that the particles can't escape and new particles can't enter, so the concentration is the same and the rate of reactions have to be the same. Now this is actually a problem because especially if you're in a factory and you're trying to make ammonia, which is used in many chemical substances, you aren't able to maximize your yield because at a certain point the concentration of ammonia becomes constant. So we've developed several processes which we've developed the Haber process, which helps counteract this. It helps to maximize the yield. But before we even discuss the Haber process, we actually need to take a look at equilibrium and how we can shift the equilibrium. So the factors that affect the equilibrium, basically. Right. So for the equilibrium, so the equilibrium for the previous reaction is as shown in this diagram. It's almost near the middle, but not quite. And obviously this is a problem in the industry because you can't maximize the yield, as I said before. So the question is, how can you increase the yield? Well, when a reversible reaction is in equilibrium and you make a change to the system that acts to oppose the change, so if I have the reversible reaction and it's at equilibrium, I can make a change to the system, and basically the system will actually oppose this change. So it will aim to restore the equilibrium and create a new equilibrium mixture. So this is most prevalent when we look at a few examples. Right, so here in this first instance, we'll be looking at how a change in temperature affects the equilibrium. And we'll be treating the forward and backward reactions separately, and this will make more sense in a minute. So the forward reaction, which is something we are familiar with, is nitrogen plus hydrogen, which forms ammonia, and this half of the reaction is actually exothermic, so it releases heat or thermal energy. The backward reaction is an exothermic reaction. So if I were to heat up ammonia, it would break down into nitrogen and hydrogen. So this is an endothermic reaction. Now, raising the temperature or a change in temperature actually affects both the forward and backward reactions separately and differently. Since the forward reaction is exothermic and it gives out heat, heating would actually speed up both the reactions. So heating, it speeds up both the reactions, speeds up both, but it favors the endothermic reaction because you're applying more heat, so there's more thermal energy for the ammonia to absorb and break down. So while yes, it speeds up both, but it helps this one more than the other one. Essentially, it helps the backward reaction more, and this means that by raising the temperature, you're actually reducing the yield and shifting the equilibrium to the left. So as you can see here, an increase in temperature will actually shift the equilibrium to the right, and it will reduce the yield of ammonia because it favors the backward reaction. And if I were to decrease the temperature, the equilibrium would shift to the left. It will shift more to the left, and this would increase the yield of ammonia. Yes. Now notice here that over here temperature, we are looking at how temperature affects the yield, but if I were to use too low of a temperature, it would actually make it so that the reaction rate is so low that it takes me too long to reach equilibrium, and that's not a good thing, especially in an industry. That's just as inefficient as a low yield. And we'll look at how we deal with things like this in practice when we cover the Haber process. But let's go on to the second factor that affects equilibrium, or the second factor that can change the equilibrium or shift it, that being a change in pressure. Right, so the second factor that we're considering is a change in pressure. Now, this is a bit interesting because a change in pressure means that you're forcing more of a gas mixture to occupy a smaller volume, and this actually favors the forward reaction, and I'll explain this using a diagram in a bit. Right, so as you can see here, this is the forward reaction where I have N2 reacting with 3H2O to form 2NH3. On the reactant side, I have 4 molecules, 1, 2, 3, 4, and on the product side, I have 2 molecules. So if I were to increase the pressure here, which would involve adding more than 4 molecules, so as the molecules here increase, the rate of collisions will also increase, or the frequency of the collisions and effective collisions will increase, resulting in a greater yield and a greater rate of reaction. However, a change in pressure for the backward reaction would imply the following. Right, so if I were to change the pressure for the backward reaction, more molecules on the right of the reaction, so more ammonia molecules, yes, the pressure would be high, but the yield would actually fall. So really you should increase the pressure for the reactants, and this will make it so that the equilibrium shifts to the right, and so your yield increases. And now we can move on to the third factor that can shift the equilibrium, that being a change in concentration. Right, so when we look at the how a change in concentration affects the equilibrium, you're basically talking about changing the concentration of ammonia, where if I were to remove some of the ammonia after it has been formed, the closed system of the reversible reaction will actually make it so that more nitrogen and hydrogen react to form ammonia in order to restore the equilibrium. And so by reducing the concentration of the ammonia, I'm increasing the yield as shown here. So it will increase the yield. It's going to shift to the right. That's what a decrease in the concentration of the ammonia does. Right, so now we come on to the final change that can shift the equilibrium, which is using a catalyst. Now we all know that a catalyst speeds up the rate of reaction, and that's what happens here as well. A catalyst is going to speed up both the forward, and the reverse reactions equally. So they'll both see an increase in their rate of reactions, which will obviously make it so that you reach the equilibrium faster, which is good in an industry because it improves your efficiency and you can carry out your processes quickly. However, a catalyst has no effect on the position of the equilibrium. So the equilibrium itself won't change, and so it doesn't affect the yield. Rather, it just makes it so that you reach the equilibrium faster. And that's the only effect a catalyst has in reversible reactions. Also, a quick note, a reversible reaction is not the same as a reverse or backwards reaction. That's because a reversible reaction is, as we defined before, it changes direction of the reaction. It's a reaction where you can change the direction, but a reverse or backward reaction is basically just one half of a reversible reaction, if that makes sense. But that's just a small note. Now that we've discussed the actual factors that can shift the equilibrium, let's look at the theoretically correct optimum conditions for producing ammonia. I'm saying theoretically because we'll be doing the Haber process later on, and you'll see a few different results there. But as of now, theoretically speaking, in a closed system, you need to use high pressure, as we've discussed before. High pressure, you need to remove ammonia as it is formed, remove the NH3. You also need to use a moderate temperature, because remember, if your temperature is too high, then you're reducing the yield because it favors the backwards reaction. But if it's too low, then the reaction rate will be too low, regardless of whether or not you use a catalyst. And speaking of catalyst, you use a catalyst, moderate temp, and you use a catalyst. And so these are the theoretical optimum conditions for producing ammonia. But practically speaking, the conditions are different, and you'll find out about this when we cover the Haber process in a few minutes. Right, I mentioned this before as well, but I want to reiterate this. The rate of the reaction for the reversible reaction will obviously be increased by an increase in temperature, an increase in pressure, and by using a catalyst. And these apply to both the forward and reverse reactions, obviously. And you need a fast rate of reaction to reach the equilibrium quickly, but you also need to keep in mind that the rate, regardless of whether the rate of reaction is high or low, that itself doesn't have any effect on the yield. So I could have a fast rate of reaction, but I could still have a very low yield of ammonia. So I need, in a factory, you try and find a balance where you can meet both ends, which is why these specific conditions aren't really practical, especially when you start taking cost into account. And with that, well, that's a good segue to get into the Haber process, which I've been mentioning a lot as of late. Right. So here we have a diagram explaining the Haber process, and there's a lot to unpack here, so let's begin. So before we even begin with the Haber process, we need to first understand that obviously the reactants are hydrogen and nitrogen gas. So we need to understand how we can obtain these two gases, both of these gases. So for hydrogen, there are two ways. You can either react natural gas with steam. It's not just water, it's steam. So the reaction only occurs because the water is hot, basically. So you can react the methane or natural gas with steam in the presence of a catalyst to give you carbon dioxide and hydrogen gas, and you can use the latter in the Haber process, or you can also obtain hydrogen from the cracking of a hydrocarbon, such as ethane. So in the presence of ethane, if you were to crack it, you could get ethene and hydrogen gas, and you use the latter. To obtain nitrogen, that's relatively easier. So air is actually already 80% nitrogen. Right, as I was saying, the air is already 80% nitrogen. And so you can actually obtain rather, you can separate the nitrogen from the oxygen, which makes up the other 20%, by burning hydrogen in air. What that does is that the hydrogen and oxygen react to form water, and you're left with just the rest of the nitrogen in air. And you can use this in the Haber process. Now, the very first step in the Haber process, or the very first compartment, involves, okay, first you pump the two gases into a compartment, and obviously the gases are mixed. You also scrub the gases, which means that you remove any other impurities from them. Then the gases go to the second chamber, where the gases are compressed to have a pressure of 200 atmospheres. And it's pumped again into the converter, which is the largest chamber, and it has several beds of iron, which acts as a catalyst. Iron is a transition metal, and in the Haber process, it's the catalyst. This iron is heated at 450 degrees Celsius, and remember the pressure here is still 200 atmospheres. And this catalyst helps speed up the rate of reaction, and over here the reaction between hydrogen and nitrogen occurs to form ammonia. And then finally you have the cooler, which basically condenses and pressurizes. Right, so then the ammonia is cooled in the fourth chamber, where it's condensed, and you basically have liquid ammonia, which can then be tapped off. Now, at this point, you'll have your NH3, obviously, but then you'll also have some unreacted nitrogen and hydrogen gas. And this unreacted gases can actually then be reused through this pipe, where they come back into circulation and can be converted again. Now, one thing to note here is that this reaction, or the Haber process, only has an efficiency of about 30%. However, because you're reusing the unreacted gases, effectively speaking, it is 100%, but 30% is its actual efficiency. So the reason that the Haber process improves the yield of ammonia relative to what we discussed before is because it has certain chosen conditions that might be different from what we discussed before. So firstly, let's talk about the temperature and pressure. Right, so when we consider temperature and pressure in the Haber process, theoretically speaking, at point X, where the temperature is 350 degrees Celsius and the pressure is 400 atmospheres, you will have the highest yield. But if you were to take into account number one, the cost of maintaining such a high pressure, the safety concerns regarding storing so much ammonia under such high pressure, and also the speed of the reaction, because 350 degrees Celsius in this case is a really low temperature, giving you a very small rate of reaction. Right, so when you take all of these into account, the best, the sweet spot would be at point Y. And this is where both yield is relatively high, and also the rate of reaction is high, so you can reach the equilibrium quicker. Another thing that I want to emphasize is that, okay, you're using a catalyst, that being iron, which also speeds up the rate of reaction. It doesn't affect yield, but it makes it so you reach equilibrium faster. Also, even if the chosen conditions give you a relatively lower yield, the Haber process has been designed to cope with this. Because again, if you remember, the unreacted, or rather, this converter is not a closed system. So the unreacted hydrogen and nitrogen gases can be recirculated into the system. And yeah, these are the chosen conditions in the Haber process. To reiterate, you use a temperature of 450 degrees Celsius. This is because it raises the reaction rate and makes the reaction faster. And you use a pressure of 200 atmospheres because it's safer to store ammonia at that pressure, and it also saves money, as 400 atmospheres is a really high pressure, and you need really powerful pumps and very strong pipes and tanks. And yeah, if there's any fault, then it could be really dangerous. And obviously you use a catalyst, that being iron, and you also recirculate the ammonia, you recirculate the unreacted gases. So it's not a closed system, which is why, effectively speaking, the efficiency is 100%, despite being the final yield is almost 100%, despite the initial yield of 30% seeming really low. Feel free to take any screenshots, else you can easily take a screenshot right now. You can also take a screenshot of this graph. It's not a very accurate graph. You'll probably find a better version in your textbooks, but this roughly conveys the point. And now we can do the final part of this chapter, which is the contact process. Right, so here we have the contact process. Now the contact process is just the name for the process that's used to manufacture sulfuric acid, which itself is the world's #1 chemical. And the key reaction in making sulfuric acid is a reversible reaction. Now, the starting point, or the main raw materials in the contact process, are sulfur, or you can use sulfur dioxide, air, and water. So sulfur dioxide is obtained from roasting metal sulfide ores in air, or you can use sulfur, which you can just mine, and you can burn sulfur in air to form sulfur dioxide. And then this sulfur dioxide is then mixed with more air, which can then be passed over beds of vanadium 5 oxide and at 450 degrees Celsius. So the vanadium 5 oxide is an oxide of a transition metal, and it's a catalyst in the contact process. And the 450 degrees Celsius is the chosen temperature to help maximize yield in the contact process. Now, once you pass the mixture of sulfur dioxide and air, which itself contains oxygen, over the beds of catalyst, you'll see that a reversible reaction occurs where the sulfur dioxide reacts with the oxygen to form sulfur trioxide. And this is a reversible reaction, and thus we say that it's the key reaction in the contact process. Right, it's the key reaction in the contact process. Now obviously there will be some sulfur dioxide that is left unreacted, so you can honestly just recycle this sulfur dioxide by mixing it with more air and then cycling it back over the beds of catalyst. But anyway, once you have your sulfur trioxide, which is a gas by the way, you need to dissolve it in a concentrated solution of sulfuric acid, and this will form a liquid called oleum or oleum. And this oleum is then mixed with water. Now what happens here is that you can directly react the sulfur trioxide with water to get sulfuric acid. But the drawback of this reaction is that it's very dangerous, it's very violent, and it actually produces fumes of sulfuric acid, which can be very dangerous, especially in a factory. Which is why you do a two-step process, highlighted in blue here. You carry out this two-step process to make it safer. So the first part is forming oleum, where you take the sulfur trioxide gas and then mix it with sulfuric acid, or you mix it with a concentrated solution of sulfuric acid, and then you mix the oleum with water so that the sulfur trioxide can react with water safely to produce sulfuric acid. Now we can look at some of the, remember this is not a closed system either, because you're recycling the unreacted SO2. Again, the reversible reaction is the key reaction, and it will, but however it's reversible, right? And it reaches equilibrium, so it never really goes to completion. And while the efficiency, the yield may not initially be 100%, because you're recycling the sulfur dioxide, effectively your yield is 100%. And yeah, now I think we can start talking about the chosen conditions. Before we actually talk about the chosen conditions, we should look at theoretical optimum conditions for the reversible reaction where sulfur trioxide is formed. Theoretically speaking, you would use a low temperature since the forward reaction is exothermic. You would use a high pressure since there are fewer molecules on the right, and then you would remove the product, which is sulfur trioxide, to lower its concentration so that more of it will form. However, the chosen conditions are obviously not the same. You use a temperature of 450 degrees Celsius, which is quite high, and right, as I was saying, the temperature is at 450 degrees Celsius. This is because the catalyst, which is vanadium 5 oxide, is a very essential piece. However, it's inactive below 400 degrees Celsius, and it works better at higher temperatures, so 450 degrees Celsius is chosen. You also use a pressure of only 2 atmospheres. So let's write that down: 2 atm or 200 kilopascals. 2 atm, which is the same as 200 kilopascals, and you use a low pressure as you use a low pressure, but the yield is still relatively acceptable. A high pressure would be better, or a higher pressure would be better, but it would cost more. You also remove the sulfur trioxide safely by dissolving it in sulfuric acid, and obviously you use the catalyst, which is vanadium 5 oxide. And these are the chosen conditions. Again, it's not a closed system, and you're recycling the sulfuric acid, so rather you're recycling the sulfur dioxide. So the final yield is almost 99%, almost. And yeah, with that we are done with this chapter. Right, and with that we officially end this video. I hope you enjoyed watching. At least maybe you learned something, and maybe consider subscribing. Thank you.